our boundary. It's smooth. It's smooth. This sound is not reflecting back to the transducer. Okay? The beam is reflected in a different direction. Alright? The direction of the reflected echo is equal and opposite to the direction of the incident beam. Yes, ma'am.
So what type of incident is it?
This is oblique incidence.
Oblique incident.
Oblique incident because it's not hitting this boundary at 90 degrees.
Okay. With a spectral reflection.
Specular reflection. With a specular reflection. But only thing that would make this from specular to diffuse, if this boundary wasn't smooth, if this was a jagged boundary, then that would be diffuse reflection. That's the big difference between diffuse and specular reflection. What's another name for diffuse reflection, guys? Backscatter. Right? Backscatter. What's the difference between backscatter and scattering? Backscatter is gonna reflect back to the transducer, right? Scattering is not gonna reach the transducer. That's the biggest difference. That's why it's diffuse reflection, okay? Because it's actually coming back towards the transducer. Okay? Scattering is just gonna scatter at a low intensity.
Many directions, right?
Many directions, absolutely. Absolutely. Alright? Again, the angle of incidence is equal to the angle of reflection with oblique incidence. How many forms of incidence do we have, guys? Two, right? Normal and oblique. Normal and oblique. Okay? Normal and oblique, that's all we have. Normal at 90 degrees. Oblique, anything other than 90 degrees is oblique. Okay? That's why I'm trying to teach you guys in like little subsections so you know. Boom.
If it's called oblique, that means it's going to be more than 90, or it could be less than 90.
It could be more or less than 90.
Oh, okay.
Anything. 90 and 89 and below, 91 and above.
Other than 90. It would be
Anything other than 90.
90 right angle.
Okay? Anything that's not at a right angle to the you crazy. Okay. Again, guys, here's my angle of incidence equals to the angle of reflection. Right here, guys. 40. We're hitting our incident beams hitting this boundary at 45 degrees. Our angle of reflection is also going to equal 45 degrees. Okay. If I had a protractor right there, I would line it up, and we could see if I had a big protractor. All right. The angle between the incident sound beam and the imaginary line perpendicular to the boundary. This is our imaginary line right here, guys. Our imaginary line. So I always say the imaginary line is where if we were creating perpendicular incidents, that's where your imaginary line is. Okay. That is called the angle of incidence. So this angle right here, guys, this little angle right here, that is the angle of incidence because it's on the side of our incident sound beam. Okay. The angle between the reflected sound beam and the line perpendicular to the boundary.
Angle of reflection.
This is our angle of reflection right there. Okay.
It's called reflection because it's reflective.
Right. It's the reflected. Remember,
So this is the main, and then this is
Right, this is
reflection of that.
yeah, this is the reflection of this beam right here.
Okay.
Our incident beam is our reflected beam is going to go at the same equal angle that it was that the beam hits the barrier. All right, right, Mr. Seth?
Yeah.
Indeed, it is true.
Sometimes I close my eyes to focus on the sound.
So you are
You telling on yourself.
Huh?
You telling on
You
yourself.
are sleeping.
Okay. All right, guys. So that was concerning reflection. Now let's talk about transmission with oblique incidence. Transmission with oblique incidence, guys, is just refraction. Okay. All right. So when a sound beam strikes an interface at an oblique
Angle.
God, this is what happens when you're working at 2 o'clock in the morning right here. When a sound beam strikes an interface at an oblique angle, transmission of any or all the beam is uncertain. We know this, right? Because we're hitting a structure at oblique incidence. Again, it's too complex for us to predict the amount of intensity that's going to be reflected or transmitted. Okay, that's why it's uncertain. All right. If part of the wave is transmitted, the wave might travel straight ahead. Okay, it may travel straight ahead. If the sound, well, I will get there. I'll get there. Okay. The beam might bend or change direction. When that beam bends or changes direction, That's called refraction. Okay? When that beam bends or changes direction, we're going to talk about the determining factors of refraction in 1 second. All right. So, the only example I could give you, because both light waves and sound waves refract, I only could give you what it would look like in a light wave, because we can't see sound waves, right?
Right.
Bang, bang, there it is. So, refraction is the change in direction of wave propagation when traveling from one medium to another. What two mediums are they traveling from to?
And liquid.
Air to water, air to liquid, right? Okay. And that's why, have y'all ever noticed this?
Yeah.
When y'all looking, like when you looking, even if you look at a fish tank, if you catch the fish tank at an angle at that corner, it'll look like the fish is on both sides, right? So that's refraction right there. That's refraction right there. Okay? Refraction is the process associated with transmission, with oblique transmission, right? Not normal incidents, oblique. Okay? And it occurs with light waves and sound waves. Right here. This guy, now I understand why I wasn't able to catch fish back in the days. You know, I'm in there, old school fishing. Oh, that's me right there, guys. That's my selfie right there. Because this guy here he's looking through air, but now he's looking through water, say shallow water. He thinks the fish is here, but the fish is actually right there because of the refracted light. Okay, so when he throws his spear, he ain't never gonna catch a fish.
Say hey, hey, hey.
He out of there all day. He gotta be quicker than that, like that commercial. Every time the dude on the fish hook, gotta be quicker than that. All right. So essentially, refraction is oblique transmission with a bend. Okay, that's the main thing. I want you to know that refraction is transmission with a bend. Guys, refraction is transmission with a bend. Okay.
It in the test.
Bend like this or change and the
With the
angle.
bend, meaning it's not coming in that straight line. It's not in. See right here.
Yeah.
This is our incident sound. This is our medium right here, right? That's our medium. This line is our medium right here. If this right here would be is a perfect transmission, right? A perfect transmission. But when it changes directions, because remember that's what refraction is, a change in direction of wave propagation.
Yeah.
See it right here? Boom, it changed direction. Right there. So that will be our refracted beam right there. That's our refracted beam, is when it changed directions, when the two mediums are different. Okay. Refraction occurs under two conditions, guys. It must meet two conditions for the beam to refract. Okay. Number one, oblique incidence. Beams are not going to refract them with normal incidence. If it hits a structure perfectly perpendicular, at a perfect right angle to, orthogonally, what's the other one?
Right angle.
I didn't say right angle.
No.
Right angle to, then we're not going to get refraction. Refraction only occurs with oblique incidence. See right here? See how this is straight? This is normal incidence, right? Of our pencil going into the water. That's why it looks like it's in a straight line. It's not going to refract with normal incidence. With oblique incidence, it's going to refract. Okay? And also, the propagation speeds of the two media must be different. Okay? So, what you see, I think I put it down here somewhere. Right here. See, we got air right here. Remember, our propagation speed for air is approximately 330 meters per second. Okay? Our propagation speed for water is 1,480 meters per second. Okay, that speed difference and that oblique incidence is what's going to cause refraction. Okay, so that's like sometimes refraction can actually lead to lateral displacement of anatomy. Okay, it can actually make the anatomy look like it's on the side of. Like if you're sometimes when you're doing biopsies, sometimes that needle can look like it's refracted. Right, if they come in there at an angle to the beam, okay? Like if they're going from a muscle layer, because you can see it coming from the muscle layer to the fat, all the way to the soft tissue. Sometimes it appears as it's being refracted. It won't appear in a perfectly straight line. It'll appear like the needle, and then it'll be offset laterally, side by side. Excuse me. Okay? So if transmission occurs and the above two conditions are met, the sound will never travel in a straight line.
What will be?
Of course.
Refraction.
Of course. It's not going to travel in a straight line. So so that's like saying that right here, these two have different propagation speeds, right?
Mm-hmm.
But it's not at oblique incidence. Okay? Also, even though they have different propagation speeds,
No, same.
that's it. Even if they have the same propagation speed, such as right here, say this right here, this medium and this medium have the same propagation speed, then it's going to travel in a straight line. It's going to look just like that, even though it's at an oblique incidence, right? Okay. It's all about propagation speed difference when we're talking about refraction and hitting it at an oblique incidence. Okay. I know this chapter is heavy, guys. That's why I don't want you guys to be focusing so much on laws and decibels. This chapter is heavy. I think I went through like 40 slides already, right? I think I made this. I think I have 98 slides for this chapter, and I originally had like 115 or something. All right. Remember, I said that's why I divided this into 2 parts. All right. So for refraction to occur, we need oblique incidence and different propagation speeds of 2 mediums. What is the other term I told you guys before refraction? How did I tell you?
Transmission, then
Transmission with the bend. Okay. It's transmission with the bend. Yes, ma'am.
I just want to make sure I understood. The 2 mediums would be, in this case, the air and the water?
Air in the water, absolutely. Air in the water. I know it's light, right? You can't really see it, but that says air right there, and it says water. I know it's real light. I tried to use the sharpness and make it darker. I couldn't. All right. We're good. We're good there, guys. So real quick. What's going to determine reflection with normal incidence?
The angle?
What's normal incidence? What's going to determine reflection with normal incidence?
is the degree.
The difference between
Medium?
2 mediums.
Impedance. There it is, right there. I'm waiting for one word. I just want to hear one word. That's the main word. Impedance differences.
Oh.
That's gonna affect the reflection with normal incidence. Okay. Remember, with oblique incidence, we can't predict how much is gonna reflect back or transmit. Okay. But if we have oblique incidence and a difference in propagation speeds between the 2 media, then we're gonna get refraction. Okay. So in clinical ultrasound, the sound beam will bend usually a few degrees at a soft tissue and fat interface. Okay, why? Why is that? Right, because their propagation speeds are very similar, right? Soft tissue is what, guys? Come on, guys.
1.54
millimeter per micron.
Ooh, that's one. I love it. 1540 meters per second. A mile a second is how fast sound is traveling. A mile a second is how fast sound is traveling. Fat is traveling faster or slower than that. Remember, that was a test question.
slower.
Slower, right? Slower, right?
Going down.
But it's not much slower. So that's why the bend between those 2 interfaces is not going to be that much, because they're very close in propagation speeds. Okay? Or a soft tissue to fluid interface, also, or a muscle to blood interface, though all of those are very close, right? All those are very close. So we're not going to get a big bend. Okay? We're just going to get a little small bend. All right? Okay? The bending occurs because the speed of soft tissue in these media are similar. I'm sorry, the speed of sound in those media are similar. All right? Bending is greater at an interface between bone and soft tissue. Right? What's the propagation speed of bone, guys? Y'all remember? In bone? Isn't it like 4,000? Isn't it about 4,000 meters per second? Somebody look that up for me. Isn't it about like 3,500, 3,400, something like that? Just about 4,000, you know? Right? That's table. 3,500, okay. So that big difference in, thank you, sir. That big difference in propagation speed between bone and soft tissue, bone being 3,500, soft tissue being 1,540, that's going to create a greater bend. The bigger the difference between the propagation speeds, the bigger, the larger the bend. Okay?